Okay, so in this video I'm just going to have a look at linear transformations using matrices. Now I'm going to do three types. I'm going to do a dilation of a point, or vector if you like. I'm going to do a rotation through a particular angle, and I'm going to do a reflection in a line. So the first one I'm going to do is a dilation, or a kind of a stretching of a vector if you like. So I'm going to take the point 2, 3 on the coordinate plane, and I'm going to stretch that or dilate it by a factor of 3. So the way I'm going to do that is I'm going to write down my transformation matrix. So what will actually stretch this by a factor of 3? Well, remember this is my x column here and this is my y column here, so I want to do something like this. We'll see how that works in a second. Now I'm going to multiply that by my point. So I've got 2, 3 here. This is my point 2, 3. What will that actually do? Well, this is a 2 by 2 matrix. It has 2 rows. So if you notice, this has 2 rows and it has 2 columns. So this is a 2 by 2 matrix. This here is a 2 by 1. This is a 2 by 1 matrix here. So remember from previous videos then, we know that we should end up with a 2 by 1 matrix here. So if I just write that in here, what I should end up with is a 2 by 1, so 2 rows and 1 column. Now if how do I do this? Well, I'm going to multiply the 3 by the 2, which will give me 6, and then the 0 by the 3 and add that, so that will give me 6 plus 0. Now do the same here. 0 times 2, which is 0, plus 3 times 3, which is 9. So I end up with the point 6, 9. Now if we just have a look at that, I think I have that here. I've drawn it here on Geogebra. So if you just have a look here, this is our origin here. This is the point 2, 3, and I've got Geogebra to actually do this for me, and we've ended up here at this point here. This, you can see here, is a dilated point, or the image of A, by a factor of 3 from B. So you can see that the distance from the origin to the image, A prime here, is 3 times the distance from the origin to my object point here, A. Okay, so that's the first one. Now let's have a look at another one of these. Let's take 2, 3 again, and this time we're going to do a minus a half dilation. So we're going to do minus a half dilation. So how would we do this? Well, you do the same thing again. We just take our transformation matrix. This time we're going to dilate it by minus a half. This is going to be 0. This is going to be 0. We're going to put in minus half here as well. We'll put in our point here, which is 2, 3. And let's just multiply this out. So we'll get a half times 2, minus a half times 2, which is minus 1, plus 0 times 3, which is just 0. Do the same here. 0 times 2, which is 0, plus minus a half times 3, which is minus 1.5. So what we end up with here is minus 1 plus 0, which is just minus 1, and minus 1.5 here. So we should, our final point will be minus 1 minus 1.5. And again, I've done that on this diagram here. You can see that you've got A here is our object point 2, 3, and we've done a dilation using Geogebra here, and we've ended up down here. this is dilated by a factor of minus 0.5 from B. Okay, so let's move on to another type of transformation then. So this time what we're going to do is do an anti-clockwise rotation through some angle. So we're going to go anti-clockwise. An anti-clockwise rotation. And the rotation I'm going to do is through 60 degrees. So we're going to take our vector and we're going to rotate it anti-clockwise 60 degrees. Now the vector that we're going to use this time is this vector here. Now I'm not going to prove this, but I'm just going to give it to you for use. It's going to be cos of theta minus sine theta, and cos theta. This is the vector we're going to use. Now we're going to rotate this 60 degrees here is our theta here. So whatever you want to rotate it through, anti-clockwise through, you put that angle in here. So in our case then we're going to end up with the cos of 60 degrees. So the cos of 60 degrees, the reason I picked 60 degrees, it's a handy kind of angle, it's one of these special angles. So the cos of 60 degrees is half. The sine of 60 degrees is root 3 over 2, and we want minus the sine, so it's going to be minus root 3 over 2. The sine of theta, the sine of 60 degrees, is root 3 over 2, this time positive, and the cos again is a half. So this is the vector we are actually going to use to do our transformation. Now we're going to take, this time I'm going to take a different point. I'm going to take the point root 3 and 1. So in other words, my x value is root 3 and my y value is 1. So it will look something like this. So if this is 1 and this is 2, root 3 is roughly 1.73, so it's roughly here, and then we'll have, let's say, 1 here. So I'm going to take this point here, this vector here if you like, and I'm going to rotate that through 60 degrees in this direction here. Okay, so let's just do that first. Let's see, so we're going to take a half root 3 over 2 minus root 3 over 2 and half. This is our transformation vector, and we are going to use the point root 3, 1, this matrix here. So what do we get if we do this? Well, we've got to take half, multiply it by root 3, so that'll give me root 3 over 2. And then we've got to multiply this by the 1, so it's minus root 3 over 2 times 1, which is minus root 3 over 2. Take this root 3 over 2, multiply it by root 3, that'll be 3 over 2. 3 over 2 here, plus a half times 1, which is just half. And if we just finish this off then, well, root 3 over 2 minus root 3 over 2 is just 0. And this is 1.5 plus a half, which is just 2. So my final point, if you like, is just going to be 0, 2. So we should end up here somewhere on the y-axis. Now, I picked this for a reason. If you have a look at this here, this is root 3. Out as far as here is root 3. From here to here is root 3. From here to here is 1. The tan inverse of 1 over root 3 is actually 30 degrees. So this angle here is actually 30 degrees. We're going to rotate it anti-clockwise by 60 degrees. That's what we said this matrix here should do. And we have actually ended up, 60 plus 30 is 90, so we should end up on the y-axis. And we see we have ended up on the y-axis. And actually, if you use Pythagoras' theorem here, this is root 3, this is 1. If you use Pythagoras' theorem here to work out this distance here, you will find that the vector, the modulus of this vector here, the distance from the origin for this position vector here is actually 2. This distance here is actually 2. So this will work out correctly for us. So we just have a look. I've done this on, or I'll do it on Geogebra as well. Let me just work through this. Okay, so we have our grid here. We'll put in, I'll just put in the point here first of all. So our point is, let me just work through this. Our point is going to be 3 to the power of half, 0.5. That's square root 3. That's our x value, and then our y value is 1. So Geogebra has plotted this for me here. So here we go. Now let's just draw this vector here. So if I start at the origin here and draw this vector out to A. So this is my vector here. Now I want to rotate that, so I'm going to use this function here. So I'm going to rotate it about a point. So we're going to rotate from here to here, and let's rotate it. We want to rotate 60 degrees, so I'll just put in 60 degrees here. Press OK, and it should do it for me. And you can see we've ended up from here out to here at the point 0, 2. So this is the point A. This is the point A prime. It's A rotated by an angle of 60 degrees. So that's what we got when we did it manually as well. Okay, so let's move on to the final type of transformation that I'm going to do, and it is a reflection in a point. Now again, I'm going to give you a matrix here, and I'm not going to go through where I got it from, but it's one you can use. So the matrix, this is going to be, what did we say, reflection in a line, and this is y is equal to kx. So it can be, k is some constant, so this is reflection in some line that goes through the origin, and it has some constant here, k. So y is equal to 3x, y is equal to 5x, y is equal to 0.2x, whatever it may be. So the matrix that you're going to use this time will look like this. Our value here is going to be 1 minus k squared over 1 plus k squared. Again, don't worry where this has actually come from. Over here we've got 2k over 1 plus k squared. Down here we've got 2k over 1 plus k squared, and here we have k squared minus 1 over 1 plus k squared. Okay, so it looks kind of complicated, but it's not really. These two here are the same. These two here are almost the same, with the 1 minus k squared just switched around. The denominators are all the same, 1 plus k squared. Okay, so this is what we're going to use. Now we're going to reflect a point. I think we'll use 2, 3 again. So we're going to reflect the point, or the position vector 2, 3 in the line y is equal to, let's say, 3x here. Okay, so let's just work through that. Now our k here is 3, so we're going to put 3 into all of these and just work out what our actual transformation vector is. So let's just do that first. So let's work out the transformation vector. So it's going to be, I'll do it down here. So let's see. We're going to end up with 1 minus 3 squared. Well, 3 squared is 9. 1 minus 9 is 8 over 1 plus k squared. Well, 3 squared is 9 plus 1 is 10. So our denominators will all be 10. You just have to work out the numerators. Okay, so over here we've got 2 times k, so 2 times k, that's 2 times 3, which is 6. Here we've got 6 as well, and here we've got k squared minus 1, so that k squared is 9, 3 squared is 9, minus 1, 8. Actually up here I should have said this is 1 minus 3 squared, 1 minus 9, which is minus 8. This is actually a minus here. Okay, so this is our vector. I'll just simplify that. So here we've got minus 4/5, here we've got 3/5, here we've got 3/5, and here we have 4/5. So this is the vector we're going to use. Now we're going to translate the point vector, the position vector 2, 3. So let's do that. So we're going to take minus 4 over 5, 3 over 5, 3 over 5, and 4 over 5, and we're going to multiply that then by our position vector, our point 2, 3. So let's work through that. So we have minus times plus is going to be minus 4/5 times 2, so that's 8/5, 8 over 5, plus 3/5 times 3, so that's 9/5. Okay, now here then we're going to do these two and these two here, so it's 3/5 times 2, that's 6/5, plus 4/5 times 3, 3/4 is 12 over 5. So this is our final point. So it's minus 8/5 plus 9/5, so that will give me 1/5, and here you have 6/5 plus 12/5, that's 18/5. So finally our final point will be 1/5, and this is 3 and 3/5. Okay, so that's it really. When you take the point 2, 3 and do an axial symmetry in the line y is equal to 3x, you get the point 1/5 and as the x value and 3/5 as the y value. Now let me just see, do I have this here somewhere? I have that here, I think. Let me just see if this will open for me. Okay, it's just loading now. This is it here. So you can see we had the point, this is our line here, y is equal to 3x, and this is the original point 2, 3 here, and you can see here this is the image C prime here, and this is, it says C mirrored in F, so it's just axial symmetry in this line here. And we did get the point 2, we got 1/5 here, and we got 3 and 3/5, which is 3.6. So our manual efforts are the same as this automatic effort here. Okay, so that's it. They're the 3 types of transformations I want to do in this particular video.